I think there should be still 20 students joining, so wait for 1 minute. Okay. Okay, so we should begin. I think there's still not many students joining. Let's take attendance first, okay? Okay, let's finish a recap of what we discussed last time, and then we'll take attendance. Right. And so last time we mentioned that you can have a subnet mask, right? So basically, if you look at IP address in binary form, okay, I think we can go to the previous slide. If you look at your IP address in binary form, right? So the first segment of it is so-called a subnet mask, okay? So which means, hey, these are the subnet, okay? It's like the subnet ID, okay? This is your host ID, basically, okay? So your IP address can be divided into two parts, okay? And when routing your packet to you, right? So it will check whether you are in this subnet, okay? And because of this reason, maybe, there are multiple entries in the router to your subnet, okay? Because the subnet ID may be different, right? So this one may have subnet mask has this, another has this subnet mask, but it sees, hey, this address of yours is also valid, right? So there could be multiple valid routing entries, okay? So if that is the case, we told you that we have the longest prefix principle. So for example, here, if you look at the subnet mask, right? So there's no subnet field, right? Because everything is zero, which means every bit is for the host. Okay. In that case, everything can be routed here, right? Including this IP address. And then we see, hey, for here, the first byte is as a subnet, right? It's 18, right? This is 128, right? So this is not a good match. We will not route to here. If you look at the third one, these first two bytes are subnet, right? So, and then we see, hey, this is the same. We should also route to here according to the criteria, okay? And finally, if we look at this one, and we told you that this is one more bits one, right? And with 7 zeros, okay? So if you look at here, this is the same, okay? So if you look at this third byte, the first bit is 1, okay? So that basically tells us that, this is also a if you look at here, this is also a valid one, right? So it's the same match, at least till the highest bit in the second byte matches. Okay, so you should go there. Right. And similarly, here the first 3 bytes are matched. Okay, you should also go. One more. Let me fix that. 5. Okay. Right. So you can see that they are perfect matches. And so we can see, besides the second entry, we can match all of them. Right? So how do we decide which subnet we should forward to? Right? And the answer is this one, right? Because this is the answer is this one, because this is the longest. Right? We have 3 bytes, entire bytes. Okay? This is 2 bytes plus 1 more bit. Okay, so we should forward to this place. So that's what we have here. Right? Longest prefix match. Right. Okay, so next let's take attendance, because I think today the attendance is not very good. Okay, Prince?
I'm here.
Okay, I see. Clinton?
I'm here.
Okay. Steve?
Here.
Okay. Alex?
I'm here.
I'm gonna lose my mouse. Okay. Ryan?
I'm here.
Okay. Joe?
I'm here.
Quinton? Quinton Coley? No. Alex? Alex? No. Michael? Michael, are you here?
Here.
Okay. Matt?
Here. I'm here.
Caleb? Caleb Edward? No. Jacob? Jacob, are you here? No. Cass, are you here? Cass? No. Diego? Diego, are you here?
I'm here.
Okay. Alex?
Right here.
Okay. Kareem?
I'm here.
Okay. Rachel? Rachel? No. Corey? I see a chat.
Hey, I'm here.
Okay. I think Jacob is here. Okay. Alex?
Yeah, I'm here.
Okay. Michael? Michael Hood? No. Jackson? Jackson Hyde? No. Cameron Jones?
I'm here.
Okay. Daija, are you here? Daija? No. Amanda?
I'm here.
Okay. Jialing?
I'm here.
Okay. Evan? Evan Landers?
I'm here.
Okay. Anne? Anne? Am I pronounced correctly?
It's on Lee.
Only, sorry. Okay. You're here, right? Only? No? Tarina Lin?
Here.
Okay. Francis?
I'm here.
Oh, sorry, Dr. Yeah, my mic wasn't working. I'm actually right here.
Oh, okay. Got it.
Yeah, my mic wasn't working. That's my bad.
Understand. Okay.
Did you call me already?
Let
Daniel?
me see. You see your name crossed? If not, probably not. Okay.
Okay, no, I don't see it.
Okay. Let me see. Jackson Man?
I'm here.
Okay. Brooke?
I'm here.
Okay. Stephanie? No. Andrew? Logan?
Yeah, I'm here.
Okay. Let me see. I think there's another student. Andrew is here. Let me see. Okay. I think I should already take. Nicholas?
I'm here. I'm
Okay.
here.
Luke?
I'm here.
Okay. Daniel?
I'm here.
Okay. Darian?
I'm here.
Okay. Free?
Here.
Okay. Swapnil?
Here.
Okay. Barraj?
Here.
Miller?
Here.
Avine?
Dude, he
Okay.
called it.
Avine?
Here.
Okay. Andy?
I'm here.
Carlos?
Here.
John?
Here.
Okay. Brooklyn Rush? No. Jack? I see chat. I think should be fine. I didn't call the name. Jack Sanchez? No. Emmett Emmett Smith.
I'm here.
Okay.
I'm
James.
here.
Got it. James. James Sobe. James. No. What? What?
Here.
Got it. Rana.
I'm here.
Okay. Angus.
I'm
Are
here.
you? Got it. Okay.
Yeah.
Yeah. Next time maybe we will also take attendance at the beginning of the class. Okay. So yes, at least no later than 5 minutes, right? So we've been waiting for more than 5 minutes. Okay. Yeah. I think this list I will skip for today because it will occupy too much time. Okay. Let's continue. Right. So. All right, let's begin. So so previously we talked about the longest prefix, right? The longest prefix matching principle, and so this allows you to do something like if you already allocate a segment of IP address to a institution, right? But the institution cannot fully utilize that, right? So you can get a sub-range with a longer prefix to someone else, right? And that will be prioritized in match. Okay, so this kind of like you can have a hike in a segment of a range of IP address, a small sub-range to someone else. Okay, so that's I think the reason why it's designed like that. Oh yeah, so there's a question from Andrew. Yeah, so other methods of taking attendance. Yeah, I'm already sampling today. Usually I don't sample so many, right? Just the reason is today really, the attendance is not so good, so I take a more comprehensive attendance. Okay, usually we will just take maybe 10 students. Now we'll see whether there are other methods. Okay, maybe I will use auto attendance using Zoom. Okay, but let's move on. So does the subnetting solve all the problems of class-based routing? Right. So the subnet, if you look at it, it doesn't solve the problem if you have the class C IP address, right? We tell you that class C is only more than 200, right? So 256 IP hosts that can support, right? So that will not solve it. Okay. Oh, I get Rachel. I think that's all. Apology for that. Why there are two names? Oh, because it's lab. So I will fix that maybe after class. Okay, just remind me. Okay, so the question is no. Okay, especially if you look at the class that have two calls. Right. So if you look at class A, it can be subnet, but only only a few of them because the first bar is for the subnet. Right. So and the first bit. The reason is the first bit of is 0. Right. It has to be fixed. Then you have 7 bits, but 0, 0, 0, 0, 0, and 1, 1, 1 has to be reserved. And class C is too small, okay, because we only have 255, right, 56 machines, okay. And class B is good, right? It's a good balance, 2 bytes for the subnet, 2 bytes for the host, but there are only so many, okay. We cannot, maybe we cannot support all the universities in the world. And another issue is that the routing table is still too big, right? So you think about if you have still, just think about if you cut out the 4 billion, right? Originally we have 32 bits, right? So 4 billion. But if you cut them out, you still have 2 million entries per router. Right? Just look at the subnets. Okay, if you add up subnet for A and a B and a C, right? You know that B and C has a lot, right? Especially C itself has 2 million because the first 3 bytes are dedicated to just subnet. Okay, so the solution is CIDR, right? So called CIDR, pronounced as CIDR. The full name is called the classless interdomain routing. Okay, so the key idea is that we want to get rid of the IP addresses, IP classes, A, B, C. We don't want them. Okay, we just use the bit masks for all levels of routing. So it's really that we no longer differentiate A, B, or C. Okay, we just use a so-called net mask. Okay, not subnet mask, right? So the first segment, no matter whether it's a subnet or it's the entire high-level network, right? It's the first segment is just where the network you are located, okay? And so we just use that for all levels of routing, okay? And so here again, so if you how many bits you have for the subnet mask decides how specific your routing is, right? So we can use arbitrary split now, okay? You can have maybe 10 bits for the network, and if that's too coarse-grained, you can have 20 bits, right? Whatever you like, okay? So this is basically the freedom you can have, okay? And for example, if you look at the Northeastern, right? So if you look at I think it's Northeastern University, right? So if you look at our net mask, it's really the first 2 bytes, right? It's 8 plus 8, 16 bits are for the net mask, and the rest is 16 bits are for the host. Okay, so here you no longer have ABC. You represent like this, right? So something like this, but with these set to 0. But this is the first 16 bits is really for your the net mask. Okay, so this is your network. This last is you can use it for your host. Okay, so that's the idea. All right, I see some chat. Okay, yeah, so I think I got an email, I will fix it, okay. And so aggregation with CIDR, right? So the original use is to aggregate the class C ranges, because you know that class C ranges kind of only can support 256 machines. Okay, this is too small, right? Because these are for the network, right? So in order to, for example, you want to have a company like Microsoft, definitely more than 200 machines, right? You need a multiple C range, continuous C range classes, right? We make it a continuous because when you route to Microsoft, it's clustered, okay? This range, 192 to 255, okay? So basically Microsoft will buy, if you look at how many are there within this range, there are 64, okay? 64 class C range. So now we have 64 times 256, right? And this can support Microsoft, okay? So this is larger number. So if you look at the CIDR address, right? So it's really, hey, now I don't really care about the 64C range classes. We could get rid of the C concept, okay? Now, if you look at what is 192, I told you guys that is 128 plus 64, right? So if you look at the binary, right? So this is the first bit, this is the second bit, they are 1 and 0, 0, 0, 0, 0, 0. Okay. So this is this address, and this is apparently all ones. Okay, 1, 1, 1, 1, and 1. Right. So now we are having these two ranges together, right? As for Microsoft, what does that mean? The first 2 bytes, of course, they are the same. They are the network part, right? And these 2 bytes are also network part. If you look at, right? So these are the always 1 for this range in Microsoft. And because of this reason, it's continuous. Only change the tail trailing bits. Okay. Right. So these first 2 bits are the same. Okay. So altogether we have 18 bits. Right. So the first is 8. Okay. The second is another 8. Right. And the third we have 2 bits. Right. That's 2. And they are all belonging to Microsoft. Okay? If you compute this, is 18. Right? So this dash 18 means how long, starting from the beginning, the number of bits belong to the subnet. And if you look at, really, if you look at just to remove this part, you can see, hey, these are all the ranges from 0, right? So it's starting from 0 to all ones. Meaning that within this range, every IP address belongs to Microsoft. Okay, usually you will buy this kind of consecutive ones, right? Which means you all the way the first 18 bits belong to Microsoft, right? And there will not be anything else. Whatever you change, it's always Microsoft. Okay? That's why you want a continuous bit starting from the beginning. Right? Then you can change whatever after. So this kind of representation called CIDR. Okay. Right. So again, so if you look at this, is called a classless. Right. So CIDR is C means classless. Okay. You no longer have the concept of A, B, C. Right. range. Okay, logically you can think about it as 64 C range. So the reason we have 64 is because if you look at the first 2 bits are the network, right? If you look at the server, we have 6 bits, right? And this basically says we have 2 to the power 6, which is 64. So many networks for the last byte to be free. Okay. Any questions here? I hope this is fine. Now, this is a representation of what we just discussed. Right? So if you look at, yeah. Yeah, please go ahead. What's your question? Okay, so just let me know if you have a question. Okay, if not, we will have to continue. Yeah, I see a chat. Yes, this is IPv4. Okay, so the student asked whether this is IPv4. So far, we are all talking about IPv4. Okay, IPv6 will not be in this slide. So IPv4 is having 32 bits. Okay, IPv6 will have 4 times that, 128 bits. So IPv4 here we have 4 decimals, right? Base 10 numbers. And if you look at the binary number like this, okay, you can also, this is what we just described, right? The first 2 bits are 1. Okay, all these 18 bits are for the network. Okay, so this is what it means. Any questions? If not, we will continue. Right. So now let's look at the CIDR way of the routing. Okay. Right. So here, for example, if you how to interpret. Right. So if you look at this IP address, okay, we say that the net mask is 19. 19. If you remember, this is 16. Right. We have 3 bits. The first 3 bits should be all 0. Okay. Then we still have. If you look at the third byte, we have altogether 8. Right. We still have 5 of the bits that can be free. Okay, so it means the first 3 bytes are 0, the last 5 can be free, and look at what how many values you can take. Right, to the power 5 is 32. Okay, so it's 0 to 31. Okay? Right. Because if you have 32, it's 6 bytes. Okay, so this basically gives you this range, and then we can use still 19 at mask for this address, and we know that the first 3 bits is 001 because 32, as I said, this is the 10050. Okay, and then you can have freedom. So this can go all the way from 32, which means all the cross are zeros, right, and to 63. Right. The reason we have 63 is because 64 means to the power 6. So you will have to here you still have 2 to the power 5 somewhere. Okay, it's the same as here. Right? If you do this is 101. Which is the next step. Okay. Now let's look at here. This is 64, right? As we said, 64 is really 1, 0, 0, 0. Okay. So, but we have 19. Right? 19 means here so many are also the third byte, are also the network. Okay. And again, we have freedom of 5 bits. 2 to the power 5 is again 32. So if you add a 32 to 64, this will be 96. Right? Again, we need to minus 1. 0 to minus 1. Okay, so this is 95. Right. Now, so you can see that here there's no conflict, right? So 0, 1, and here now this bit is 0, this 1. Okay. If we want to further, right? So after 95, we still have something we can work with, right? And here we will make it 18 bits, right? Which means now we just look at this here. Right? So of course we can further make it fine-grained by specify the third bit. But here in this example, we're not doing that, okay? Because it's 18, not 19. Right? Because 8 plus 8 plus 2. Okay. So if you look at 128, 128 is really 1, 0, 0, 0. Okay. Right? So if array crosses 0, this is 128, and so the largest is 1, 0, 1, 1, 1, 1. Okay. And this number is 128. Plus, I think 64, right? Because you can have, here we have 6 cross, right? Freedom, right? So we have 2 to the power 6 is 24. But of course we want to minus 1. If you don't minus 1, this is 192. But if you don't minus 1, it will increase to this one. So now you have this range, and then if you have this segment, this is 1.1. As we discussed, this is 192. I hope you are now familiar with that. 192. Okay. And so then you have another freedom. So this is 192 plus 64. Okay, is equal to 254. But we need to minus. That's why we have 255. I hope you understand how to do this calculation. Okay, so this is really 2 to the power of something. Right? You need to be familiar with it. Right? 2 to the power 1 is 2, 4, right? 8, 16. Okay, 32, 64, 128, and 512, and 1024. Okay, and maybe 2048, right? And 4096. Okay, these numbers you should be familiar. And all the way up, there's a 65336, right? This is short, which means 2 bytes are all ones. 25665. Okay, plus 16. Again, you don't have to remember to this extent, but those within the 2 to the power of 10, you should remember. Okay. Yeah, we might have IP address calculation in the midterm. Okay, so like you need to understand, let's say we give a net mask, and you need to know maybe the third byte, how many bits are belonging to the network part, how many are free. Okay. So this will be the routing table, right? So the address, and they will route to different places. And if you look at there's certain parts that are missing. And yeah, if you look at, for example, 95, we jump to 128. Right? So we missed something. What do we miss, right? So you can see we don't have 0, 1, 1. Okay, so there's an entry that's not here, but that's fine. Right? So the routing table may never see some traffic to there. Okay, that's totally fine. Maybe it's in a totally different region. Right? So we are in, for example, Birmingham, and some traffic in California. We don't care, right? So because they probably will never route to a small region in California, right? So maybe we'll route to some popular cities, LA, etc. Okay, but not to some other places. Right? So there may be small segments that's not in our router, but definitely down there to their localized area, right? The router will have that. Right? So it's possible we have some holes with no coverage. But if you ever send something there, right? So I think there's a inter-routing protocol, inter-network routing protocol. Okay, we will discuss that after the midterm. Okay, that will help you find it. So here, basically, this is the concept, the third byte, and you have part of usually you are using the third byte to strike a balance between the network bits and the host bits. Okay, and let's take a look at how the size of the routing tables, right? So how it increases. Okay, so if you look at the year, okay, this is not so up to date, right? So maybe till 2018. Okay. But you can see it's a steady increase, okay? And it's actually increased faster and faster. If you look at the curve, it's like a shooting curve, J curve, because the slope is increasing, okay? So definitely we'll run out of IPv4 address, right? So that's why in the next slide, we will talk, next set of slides, we will talk about IPv6. And I think this is already a little bit outdated. This is 700,000 so entries already. Okay, and again, this is still acceptable. Okay, right. So for a complete IP routing table, in case you really need to route to everywhere, you have so many. Okay, it's still acceptable. Okay, compared with, let's say, how many billions of people have. And it was like half in maybe 2015. Okay, and these are only required by the backbone router. Once you route to your local area, right? So you really just care about, for example, this is the backbone, right? So if you will go here, or your right to local routing table only care about the next hop is here. Okay, everything will merge to here, then they will go to different. So only the backbone need to care about all kind of directions. Okay, so that's what it means. So again, this is because our IP address design is kind of clustered, right? So if you are just going to the same second hop router, then the IP address can be clustered into a range. Okay. if somehow a sub-range, let's say they will all go to here, but a sub-range should go to another router, right? So you will make a longer prefix and then go to another router. Okay, this is the longest prefix matching principle. Okay? So here's the takeaway messages, right? The hierarchical addressing is critical for scalability. Right? So we have the hierarchies. So the continuous segment can just have one entry instead of one entry for every host there. Okay. And not all routers need all information. Right? So maybe backbone router need more information. For your local, you just need to know which outlet you go to the backbone. Right? And maybe you only have a few outlets. That's it. Okay. And so there's a limited number of routers that need to know about the chains. Right? If if you are in, let's say, Birmingham, you don't care about some localized changes in, for example, California. Okay. Until you have to communicate with them. And so there's non-uniform hierarchy useful for heterogeneous networks. Okay, so that means, for example, you can have if you don't need a lot of hosts, right? So you can have more bits for the network. Okay, and if you need a lot of hosts, you need more bits for the host. Okay, so it's totally free. Okay, the CIDR will allow you to use whatever you need. Right? And originally, if you look at the class-based addressing, we need to have in the network address in the byte unit. Okay. Now CIDR you can split anywhere, especially usually you will split in the third byte. Okay. Because you usually will not use a third and fourth byte together for the host. You don't have so many machines. Okay. So implementing there's also challenges, right? So how you think about the router, right? You need to look up your table and find all matches and find the one that is the longest prefix match, and then forward your packet, right? The IP datagram to the correct next hop router. Okay, so you think about the hardware. There's some challenge in the implementation. Okay, yeah, that's basically the end. I kind of lose control of my mouse. Okay. Yeah, now we will go to the next slide. Okay, so it seems that we are going sufficiently fast. Maybe we'll have a good estimate by Friday when we'll have the midterm exam. Okay. Let me clear. Yeah, so far we only talk about the IP address, right? So if you look at the IP address, it's just one field, right? So one field in an entire IP datagram. So remember we have the concept of packets, right? And we told you that if you are in the data link layer, we call a packet as a data frame, right? But if we are in the network layer, we call it a datagram. Okay. Anyway, it's just a packets, but in different layer we have different names. Okay, you will see that for upper layers later. So in the network layer, we call it datagram. So just keep that in mind. So IP datagram are like a ladder, because if you put a packet to somewhere, right? So the router will read the ladder and it has the source address and the destination address. It doesn't care about how it comes from, right? It just care about where I should forward to the next hop router. So your IP datagram should contain all the information necessary for the routing. It is self-explanatory, okay? So it's totally self-contained and include all the necessary information for the addressing, for the routing, okay? There's no advanced setup for connection of circuits, right? So there's no states, right? It's stateless in some way. This is like similar to our HTML, right? You have send a request, the server sends you a response. It don't track what information you have unless you log in, use Web 2.0, then you have the session. Here it's like stateless. Okay. So here let's take a look at what are in this IP datagram, right? So the IP datagram can be crossly divided into two parts. The first part is a header. Okay, we call it a IP header. The second part is called the data payload. Okay, the actual content. Right? Header is really for routing, for control, etc., because it has to be self-contained. And there's also a optional header. Okay, so you can say, hey, now I want to add additional information. So you can have the green part. That's optional. First, let's just look at the blue part, right? So the gray part is what we are talking about on this slide. Okay. So IPv4. Here we are using IPv4 as an illustration. We will see the IPv6 format also. Okay. So here the first field is version. Right? For example, we are talking about IPv4. This should be 4. Right? And there's also header length. Right? So this is how long this header is. Okay. And when we show this, this is the bits. Okay, 0 bits, 4 bits, 8 bits. Okay. So this entire thing is 4 bytes. Right. Basically. Okay. We have 5 of those 4 bytes, which is 20 of them. Okay. So, but if you look at header length, right? So it's really written in the way that how many 32-bit words. So instead of saying, hey, I have maybe 4 times 5, 20 bytes. Right? So here it will say I have 5. Okay. Because a unit is not a byte. It's a unit of 4 bytes. Okay. And you can see because of this reason, when we plot our IP header, the whole datagram. Right? So what we do is we use a width that is fixed to it. Right? Basically, everything is in the unit of 4 bytes, okay, 32 bits. And so there's another field which is called a type of service, but usually it's not used. So we can safely ignore them for now. Okay. And there's also the datagram length. Right? This is length plus of the header plus the data. Okay. So basically, let's say if this is your length, again, here is in byte, which means here we have 20 bytes. Assume that we have no additional optional headers. Okay. And the data, maybe we have 3080. So if you have this summed together, this number of bytes will be 3,900. Okay. So this is what we are saying. So the use is really, hey, now you have the header length, you also have the entire datagram length, right? You know where you split them. Okay. This is the total, right? This is maybe header plus the body. Okay. Right. It is datagram length. The header only is h length. So you know the data length. Right? It's just minus of these two. But again, this is in the 32-bit word, this is a byte. So there's a slight difference. And again, so as I said, you need to memorize this number. Right? So if you are familiar with this, so this is a 2 to the power of 16 minus 1. And because if you, not minus 1, this is 6, right? It's divisible by 2. Okay. So this is because, you have 16 bits. From 16 to 31, there's 16 bits, right? So altogether, the length can go all the way to this one. From 0 all the way to here. Okay, you cannot go larger than this, right? So this also put a limit on how large the whole packet can go. Right? Usually, you will not send it as large as this number. So this is more than enough. Okay, because we have the MTU, if you remember, right? MTU is much smaller than this. And MTU is a data link layer stuff, right? Maximum transmission unit. Okay, but MTU, your IP datagram is wrapped in the MTU, right? In the data link, data frame. Okay, right? The data link data frame add additional like Ethernet headers, right? So the MAC address, etc. Okay, it can only go longer, but this longer one cannot go beyond the MTU maximum transmission. If you remember what we discussed last time. Okay. So this is way more than that. And so there's also a concept, right? If you look at the third row, which is another 32 bits, right? So there's a TTL, okay, TTL. So this is called a time to live, this is TTL, okay? So this is decremented whenever you pass a router. For example, you say, I can allow it to go at most 10. I pass a router, this data frame will come here, but this field will become none. Okay? Next time you pass another router, it will become 8. Okay? Why we wanted this? This is because, there could be some routing issues in the routing table. Somehow give you a loop and it will stay there forever. Okay? If this misconfiguration or some issues happen, right, there are only 2 choices. The first choice is that if someone is sending, these packets will stay looping forever, cause congestion. Okay? The second is just if you find that it's go for many hops, you dropped it, okay? Then you will eliminate. Of course, the second one is better, right? The first one will go on forever, so the network will finally, you cannot use it. It will be totally garbage, right? You cannot transmit anything. It's all like a field with those kind of things. Okay, so that's why we need time to live. Okay, when it comes to 0, let's say you go, and the packet is minus to 0, and you reach this router. This router will not continue, because if continue, it becomes -1. Right? It will just drop it. Okay, this avoids an infinite loop. And this is actually some routers may even be more friendly. It will tell you, hey, I find its TTL becomes 0. You cannot continue sending, right? It's failed. It will give a negative acknowledgement. Okay, then that's even nicer. Otherwise, usually the sender, if you are running a TCP, for example, on top of the IP, you will find it's timeout. You will resend again. And if you try maybe 16 times to find it failed, then you know it's not working. Okay, then you will just give up. It's unreachable. 404 error in your HTML. HTML application protocol, by the way. Okay. Implement maybe using TCP, and then all the way to IP, and then IP will find, hey, this get up to 0, it's not reachable. It will all the way then come up to the protocol. Okay. Next is a protocol for the IP, right? Because IP is a network layer protocol. You can do TCP, UDP, ICMP, etc. A lot of transport layer protocol. Right? So what the encapsulated, right? The encapsulated protocol is here. Okay, it's another header. Let's say IP header here, then this is data header. Right? Okay, there could be some application level header and then application protocol. Okay? So that's why we call it encapsulated. Right? So the encapsulated protocol is really here. It's the transport layer. And the 6 is for TCP. If you see 6 here, it's TCP. 17 is UDP. Okay. Finally, you have a checksum. Right, the checksum you can use it to just for error checking. Right, you get all the 2-byte numbers, right, summed together. Right? So for example, you have this, sum this, sum this, sum this, all the way to sum. Okay, and then you see whether the sum is the same as the checksum. This is for error checking, whether there's some bit flipped. Okay. But actually, it's not so popularly used, okay, because usually backbone is very safe. Unless you are using wireless, you might need it. Okay. And the TTL actually is used to implement the trace route, if you remember what we talked about. I see a chat. Error correction is really depending on the up-level protocol, right? So the IP layer probably will not. Okay. It's just a here for the purpose of reserve the field. Okay, by that time early days, right? Just in case you want to do the error correction. As far as I understand, the IP layer doesn't do that. Okay, the error correction is only done in the data link layer. Okay, so if you remember, we talked about data link layer. We have the parity bits, right? So we have a 2D scheme. Okay, it's only in the data link layer, especially for wireless. Some routers do the checksum. Okay, IPv4 still do this. IPv6 this field is not there because the backbone is so reliable. So we don't really need it. And yeah, so for the IP spoofing, so let me see. So for that, you can send me email. I will maybe answer you independently. Okay, so I will recommend you something to read. Okay. So here, the TTL is actually useful for trace route, right? So if you remember, we have a trace route command. We can say, hey, go to the first router and come back, right? And go to the second router, come back. The third router, come back. So in order to achieve that, what we are doing is we give you a TTL of 1, then you reach here, then the router say, I cannot forward, I come back. Okay, and you can give another TTL of 2, that will come, right? And 3, and all the way you reach the destination. Each time you increment the TTL by 1. Okay, and if you remember, we in one class very early we talked about the trace route. Right? It will send 3 of this, like a TTL1 packet, and 3 of TTL2. Okay? This is basically how trace route is implemented. Okay? It can be used to basically probe what are the routers in the way. Okay. Next, let's look at these two 32-bit. Okay. Right. So this is really simple. Right. So just like in the data link layer, you need a MAC address from the source machine and the destination machine. Right here, we need the source IP address and destination. And because in the routing table, we will look up the destination and decide which next hop router we need to get to. This is very useful. And source is also very important because finally, the receiver receives this IP datagram, right? It needs to know if it's respond to what's your source IP. If you remember, if you decide your application, it's defined by two things: IP address and port number. Port number we will go to the TCP UDP layer, and we'll talk about. Okay, but IP is also necessary. You have done the programming project. You should know that the receiver is really relying on your this is force field source IP address to respond to. Okay, and TCP is using that to establish a connection between you guys. Yeah. So this, so in principle, these are unique IP addresses. Okay, right? But in reality, it's often okay. So there could be conflicting IP address, and sometimes it can be shared, right? So like the NAT technology. Okay, we will see that. And so remember, we have the fragmentation thing, right? So fragmentation is really in the Ethernet level. Okay, we have the maximum transmission rate. And keep in mind, if you look at the data frame in the, for example, Ethernet layer, right? Your IP layer is really, it's here, okay, inside. Then you have the TCP and maybe HTTP, something like this. Okay, so it's encapsulated. Right? So MTU definitely will impact your packet. Right? So your IP datagram cannot be so long. Your data link layer frame is even longer. Okay, so then the MTU really applies. Okay, so each network actually they are running some they have the MTU concept, right? So because you think about the network layers above the data link layer, right? They have the data link layer devices with MTU. Okay, and so according to the DAPA principle, right, we have the ARPANET, which is the earlier version of internet. Right? So they have the networks allowed to be heterogeneous, which means we allow different routers to have different MTU. Okay, one router may have 4,000, another 2,000, another 1,500. Okay, so of course, if you send a big packet, right, 3,000, then you cannot send through it. It has to be fragmented, as we discussed again. Right? And if you fragment to be still like 2,000, and you reach here, you need to fragment further, like 1,500 and 500. Okay, so this is because MTU may not be known. Here we care about the minimum MTU, right? The minimum along the path, which is 1,500. Okay, but it may not be known, so we need some mechanism to handle that. Okay, I think we will continue next time because of the time. Okay, so we will stop here. So, and on Friday, we will continue with the slide. Thank you. Any questions? Yeah, we will have a review of the concepts with another slide before the midterm. Okay, I think one student is asking. So the question about a lab. So if our exam is really on Friday, we will cancel the lab. Okay, for that week, okay, for next week. But if it's on Wednesday, then we will still have the lab.
Can I ask you to clarify about the review bit? Is it going to be kind of a review session day, or
it's just a regular class? But in the class, we will have a review for what we covered so far and the key points.
Yeah.
In the midterm. Okay.
Okay. Then we'll have access to the slides too, right? Just
What?
for me. We'll be able to have access to the slides too.
Yeah, for sure. Yeah, we will release that. Okay.
Yeah, and
then you
Brooklyn's
can
here. Brooklyn Rush is here, by the way. Just a heads up. That's it.
Yeah.
Thank you.
You're welcome. I see another question. Are we expect to keep using the Cisco calls? Oh, it's gonna expire for the account. So if your Cisco account is gonna expire, just send email to us. Okay, we will see how to handle that. Right, so
What are the best resources we should use in order to study for this test? Just the lecture notes, or just the notes, or the book, or everything?
yeah, everything, but we will be more, we will be more targeted. We will have the review slide, right?
Okay, cool. Because I opened up that book and it was a little more complex than I thought it was going to be. So
Yeah, I understand. Yeah, so basically, if you follow what we teach, right, in the slides, that should be fine. But we will zoom into those important points that we might test you. Okay, just don't want to hit you surprise in the exam.
Okay.
Yeah, we are going to complete the midterm during the class. Okay, so one class will be the review. After that class, we will be the exam. Okay.
How long is the exam going to be? You said it was going to be short, but what does that mean?
It's exactly the class time, right? It's 15 minutes, right? Just like the class. Okay.
5-0?
We will not ask too many questions, basically.
All right, sorry.
But final will be a little bit longer, okay? So because there's a designated time for the final exam for each course. Okay. For the midterm, we don't have the designated slots, so we'll make it just one class. All right, so let me fix the attendance issue. Yeah, I understand. So don't nervous. Okay, prepare for the review slide, and you should be fine. Okay, we will cover. We will not hit you surprise. Okay. Okay, it seems that there's no question. So let me fix the attendance. I think one student, Rachel, somehow my browser was that, so I have to.
Did we skip any chapters in the book?
Actually, I think we are simplify the book a little bit. Okay, so the book is more comprehensive, I think. Okay. But whatever we test, we will just test what we cover. It's okay.
Okay.
Professor, can you double check me for attendance?
Yeah, let me double check. So Megan,
I'm in 534.
Okay. If somehow the server was down, okay, can you send me an email? I will handle that afterwards. Okay.
Yes, thank you.
You're welcome. Yeah, because the server seems to be down. Okay, if you have attendance issue, just send me email. I will, because it's in the email, I will not miss it. Okay, I will handle that. Somehow the Canvas server is down. This is attendance server. Okay, so it seems that you have no more questions, so I will dismiss. So just explain this. Okay, so there was error thing, return loitering. I think the server is down. Okay, I will handle that once it's in my email. I will see you Friday.